Hello everyone and welcome to 8.2 Thermal Energy Transfer video 3 of 3. This will be the shortest of the 3 videos. So this is the slide that we left off with last time. We looked at how the levels of carbon dioxide were determined, and we also made a significant conclusion here using the graph on the right that not only have the levels of carbon dioxide been increasing over the years, which is also demonstrated in the animated graph on the left, but also we saw that in the cooling months, the number of carbon dioxide, the concentration increases, whereas in the warmer months it tends to decrease. And we said that that's most likely due to plants. In the warmer months, you have more plants and they're breathing, quote unquote breathing, okay? So they're able to absorb more carbon dioxide and hence there's less of it in the atmosphere. Okay, let's move on. So we talk a lot about this radiation. Some of this radiation is coming in towards the Earth. It gets absorbed partially, some of it gets reflected, but how exactly does it get absorbed? So if you have a molecule and you shine light on it, does that automatically mean that the radiation gets absorbed? Well, not exactly. So we know that the radiation coming from the sun is coming in at approximately 1380 watts per square meter, so that's the solar constant. And of course, it might be a bit less than that if you are further away from the equator. Now, the energy coming from the sun, we can look at this from the point of view of a particle of light. Okay, so a particle of light is called a photon. Sometimes it's called a quanta of light. Quanta just means small packet, okay, so or like a particle. Okay, so let's say we've got a photon of red light. Now, red light, you know, has the longest wavelength of all of the visible spectrum light. Okay, violet would have the shortest wavelength. Now, if you recall, long wavelength means low energy. So of all the visible light, red light has the lowest energy. Now, the atmosphere, as you know, is made up of a lot of different types of gases. Now, the radiation coming from the sun interacts mainly with that first layer on the outside. Now, imagine you have some sort of molecule, okay? And so that molecule is made up of atoms, and those atoms have nuclei and they have electrons orbiting around the nuclei. So imagine a very simple model. You have two energy levels for your electron and you have your electron orbiting around the nucleus. For our purposes, this kind of setup is completely appropriate. Okay, so this electron currently has a certain amount of energy in its energy level. If it was to be able to go to a higher energy level, that means it needs to absorb a photon of light. It needs to absorb light because that'll give it energy. And that energy has to be equivalent to the gap between these two orbits. If the incoming light has less energy than the energy gap between these two, it's not going to be able to make that transfer over. So imagine you've got this red photon, and the red photon unfortunately does not have enough energy to, well, send the electron up to the higher energy level, so it just passes right through. But now let's say you've got this blue particle of light, and blue has more energy than red. Now, for our example, we say that the blue light provides enough energy to the electron that it makes the transition to the higher energy level. And we can even take this a step further and say, well, if you impart even more energy, so let's say you impart a photon of violet light, and this electron can accept it and even escape. And we call that ionization. Okay. When electrons ionize, right, when they leave the atom, this is how you get plasma in a gas. Now, those electrons, when they absorb the photon, in other words, they're absorbing energy equal to this energy gap, and they're jumping these energy levels, at some point they're going to want to come back down. They want to go back to equilibrium. And when they do go back from the higher to lower energy level, they release a photon equivalent, with the energy equivalent to the energy gap between the two levels, between the two orbits. So whatever energy that is, that's going to correspond to a certain frequency and wavelength of light. And that might be infrared, it might be visible light, whatever it happens to be. Now, what we're going to see later is that greenhouse gases have a tendency to absorb infrared wavelengths of radiation. All right. Now, when these photons end up getting released, we call this scattering. Now, there's one type of scattering that you're going to see in this slide, a few slides later on. It's called Rayleigh scattering. So you don't need to worry too much about what that is. What you need to really focus on is scattering. This is just when the photons get released by the nucleus, by the electron. All right, here we go. So this is what I mentioned earlier. Some of the scatter photons may be in the infrared region. They can be in technically any type of frequency, any wavelength. They might definitely be in this part of the spectrum. So we'll see this over the next couple of slides. Okay, so greenhouse gases. I'm pretty sure a lot of you remember that little bit of a shock from the last video that water vapor is actually a significant greenhouse gas. And as we'll actually see in a couple slides, it is actually the biggest contributor from all the greenhouse gases. So that's pretty significant. So just because you have water as a byproduct doesn't mean you're not polluting. Technically, this also falls under the guise of pollution if you're contributing to greenhouse gas. All right. Now, what we're trying to do here is understand how energy is stored inside of a molecule. Okay, so we looked at how the electrons absorb energy, but what about the molecule as a whole? Okay, so we're going to consider the triatomic molecule CO2, carbon dioxide. Now, carbon dioxide, you've got two oxygen atoms combined with a carbon atom. Now, from what you remember in early science, grade 9 science, this is a covalent bond. Now, we're replacing the covalent bonds, or rather representing them, with springs. Okay, so just stay with me for a moment. There's a reason why a spring is a great analogy for these bonds. Okay, so first things first, because you've got a nonmetal with a nonmetal, it's a covalent bond, right? This is where you share the electrons. If you had an ionic bond, this is where your nonmetal and metal join together and you have a donation of electron or electrons rather than sharing. Now, why is the spring such a good representation for the bond? Well, from what we learned in physics, we saw that you can store energy in a spring, right? Potential energy. Okay? And springs have the ability to move the two objects on either end further or closer apart. And this mimics what's actually happening in the bond. With the bond, each member in that bond has some freedom to move closer and further apart. Okay, so that's why it's such a nice representation. Okay, now heat energy. Let's talk about heat energy because that's infrared radiation is the primary form of radiation that gets absorbed by greenhouse gases and then re-emitted. Right, so now how does this thermal energy get stored in these molecules? Well, there's two forms of energy, kinetic and potential. So the potential energy is stored in these bonds or the springs, and the kinetic energy comes from three possible ways. Okay, so one possibility is when the molecule vibrates. Okay, so there's actually a couple ways to see the kinetic energy, so we'll talk more about that on this slide. Now, how do you have more or less potential energy? Well, if your spring gets extended, so if the atoms move further apart, there's more potential energy there. If they're closer together, you have a smaller potential energy. The same is true even with the Earth, right? If you recall the formula Eg equals mgh, the gravitational potential energy, if h is bigger, then you have more potential energy. Of course, h should not be so big that your g value suffers as a result, but you get the idea. All right, so something we have to keep in mind is that just because you have more potential energy and there's more distance between the atoms in this kind of a bond, doesn't mean the temperature is going up. That doesn't mean you have more thermal energy. Okay, so thermal energy is not getting stored in this particular way. Thermal energy contributes to temperature, and temperature is directly related to kinetic energy. So it's the kinetic energy that's relating to the temperature change. And like I mentioned on the last slide, vibration is just one method of storing kinetic energy. The other two methods are translation and rotation. Now in physics, even in grade 11 physics, when we first started learning about the kinematics and dynamics problems, we always only considered translation problems. Whether you were pushing a box across the floor or kicking a soccer ball across a field, even though the soccer ball is rotating and when you bring it to a stop or if it hits a wall or boundary, it technically will vibrate a little bit. We never discussed the rotation or the vibration. We always consider the problem in terms of translation. So now we're going to be considering all three. Now vibration, when you put your phone on almost silent, it vibrates, right? So it's moving back and forth along its certain direction. Okay, so vibration in this case means the molecules are oscillating in conjunction with the springs. Now, every object has its own natural type of frequency, and if you can match the frequency of that object, you can make its oscillations increase significantly in amplitude. We learned that when we studied waves. And so how is an opera singer able to break the glass just by singing a certain tune, a certain note? Because that note is the same frequency as the natural frequency of that object, as its resonant frequency. And so suddenly the amplitude of the vibration skyrockets, and it can cause this material to shatter. Now, with greenhouse gases, the natural frequency of these greenhouse gases is to absorb infrared radiation. We're going to see this in a couple of slides, how we know that this is actually the case. If it wasn't prone to absorb infrared radiation and heat, well, it wouldn't be contributing to global warming, and it wouldn't be considered a greenhouse gas, right? There are a lot more molecules and atoms in our atmosphere than these greenhouse gases. But if they don't contribute to heat accumulation and re-emission, they're not considered a greenhouse gas. All right, so we talked about vibration. Translation, the whole unit is moving in a certain direction. Okay, so like I said, that's the only thing that we considered in physics so far. Rotation, something is spinning about some axis of rotation, usually about its center of mass. Okay, so all three of these things, even at the same time, contribute to the kinetic energy of the molecule and the compound, and overall its temperature. Okay. So as promised, here we're going to see how we know that it is infrared radiation that is being absorbed mainly by these greenhouse gases. Different gases absorb different wavelengths. Okay, so for those of you that studied astronomy in the IB physics, even if you didn't study astronomy, that's fine. Most likely in chemistry, you were exposed to something called a spectrometer. And if you weren't, let me just talk a little bit about that now. Imagine you have a flashlight and you shine that flashlight through some gas. Okay, so you have some gas in a region of space and you shine light through that gas. Now, if the frequency of that light is equal to the energy level difference in some of those atoms, the electron will be able to absorb that photon of light and go to higher energy levels and do its thing. Okay, so the idea is there will be some parts of that gas that will be able to absorb the light if it's a certain compound, right? So different compounds, so if I have hydrogen gas versus helium versus nitrogen versus carbon, they're all going to absorb different frequencies of light because their atomic structure is different. Okay, so their needs for those energy levels will also be different. Now, whatever light ends up passing through the gas after, it gets processed through a machine called a spectrometer. And the spectrometer analyzes what light came in versus what light came out. Okay, so the light that came in would have all the wavelengths of light. If it's white light coming from the flashlight, it'll have every wavelength of light from red all the way to violet. It'll have everything in between as well. But after passing through the gas, maybe there are some holes in that light at different wavelengths. And based on those absorptions, we can figure out what elements and what components comprise that gas. Now, in this picture, what we're seeing is, well, you've got water vapor, carbon dioxide, oxygen, and ozone. I'll talk a bit about what ozone is in a moment. Methane, nitrous oxide, and scattering. Again, don't worry about Rayleigh scattering, just focus on scattering. So the four greenhouse gases we looked at were water vapor, carbon dioxide, methane, and nitrous oxide. Oxygen and ozone are also greenhouse gases, but they're not as bad. In fact, ozone is pretty important. Okay, so oxygen, you might remember, this is what's called a diatomic molecule. That means it doesn't occur, usually, it doesn't occur naturally in nature by itself. It's very rare to find oxygen by itself. You will find oxygen with another oxygen. It'll be O2. Okay, ozone is actually O3. And ozone, as you might imagine, is in the ozone layer. Okay, so this actually plays a very important role. It absorbs ultraviolet radiation coming from the sun. But don't get too attached to ozone because it's actually not that good for our health. Now, being where it is right now in the upper atmosphere, it's it's okay. But if ozone were on ground level, it would cause a lot of dangerous respiratory hazards to us and to our health. So let's just be happy where it is in the ozone. It's doing its job and it's happy there. All right, water vapor. What we're seeing here is that water vapor is absorbing a lot of thermal infrared radiation. Now, it does absorb also some near-infrared radiation and very little visible light, no ultraviolet. Carbon dioxide, again, most of the absorption is happening from the infrared, thermal infrared, and the near-infrared. Oxygen and ozone, same thing. With all of these, okay, these top 5 columns here, they're all absorbing mainly in the infrared, if not only in the infrared. This is why they're considered greenhouse gases. It just has to do with the natural frequency of these compounds. Okay, so we can actually put up a little bit of a bigger picture. If you add all of these together, all the contributions, you have quite a significant amount of absorption and scattering simply in the infrared region from these compounds. All right, consider the absorption graphs below. Which portion of the electromagnetic spectrum is represented? Well, you just saw it on the previous slide, but in case you didn't know, well, there's other ways you can take a look at this. If you remember that water vapor, carbon dioxide, methane, nitrous oxide, ozone, oxygen, they're all greenhouse gases, you will remember that greenhouse gases will absorb infrared radiation primarily. Okay, that's heat. Part B, which greenhouse gas contributes the most to the greenhouse effect? Okay, well, it should stand out to you in this picture. It's water vapor, and it's significantly higher than any of the other gases. Which gas is the least significant contributor? And again, looking at this, oxygen and ozone. Okay, so that's the least contributor here. And there are the answers that we just talked about. All right. Moving on. Now, over the next couple of slides, we're going to look at energy balance in the Earth surface and atmosphere system. Now, in 8.1 and also earlier in this video, we saw once again that the solar constant is 1,380 watts per square meter. This is the amount of power coming from the sun per square meter towards the Earth. But we also saw that this amount of power is not hitting the Earth equally. We saw that at the equator, that power is spread over a small area, is more concentrated, hence warmer, whereas in the north, it's spread over a larger area, and therefore it's much cooler. Okay. On average, we'll say that the average intensity of radiation hitting the Earth, okay, taking into account the large spreading in the north and the limited spreading at the equator, it's about 340 watts per square meter. So now here we go with Sankey diagrams once again. Draw a Sankey diagram for a model of the Earth without greenhouse gases. In other words, whatever comes in, all of it goes back out. Okay, so first things first, we are assuming that we have an average intensity of 340 watts per square meter. Right? This is what we saw on the previous slide. So that's coming in. Okay, so 340 joules, this is the amount of energy per second per square meter. Now, some of that energy gets reflected by the clouds. Okay, so maybe 75 joules. Okay, some of that energy gets reflected by the ground. Maybe there's snow there. Whatever there is that gets reflected by the ground. Okay, another 30 joules. Now, the rest of that energy gets absorbed by the ground. Now, the ground doesn't just absorb those 235 joules. It will eventually re-emit it as well. Okay. Now, in this case, again, we're assuming no greenhouse gases, so the 340 that's coming in, that's equal to the 30 plus 75 plus 235 going out, which is also 340. Okay. Show that at the space/atmosphere interface and at the ground/atmosphere interface, the net power flow is 0. Okay, so, well, I just discussed that. If you take 340, that's coming in, and you subtract 235, and you subtract 75, and then 30, you'll hit 0. So at this space-atmosphere interface, the net power flow is 0. And at the ground-atmosphere interface, we've got 235 joules coming in, 235 joules coming out, so it's a perfect system here. Now, In reality, this is not how it's going to work. You do also have the greenhouse gases, which will prevent some of this radiation from escaping, and potentially even these points as well. For these slides, let me actually just put up the rest of this. You will notice that in fact the slides don't end here, but we are actually going to stop there for section 8.2. So anything in any slide past this slide will not be covered and will not be tested on in any way. Okay, so you will not have any evaluation on slides on material after this slide. On Teams, I will indicate to you which pages in the textbook are relevant, and if there are any pages in the textbook reading that you need to skip, I will indicate that, if there are any. Okay, so that concludes our last video for section 8.2, thermal energy transfer.